Right, welcome to my talk. The hidden art of thread-safe programming. We're going to look at java.util.Concurrent at a level you might not have done so far. So before we start, we're going to start with the Q&A. All right? So let's hear some questions that you'd like me to answer. Because at the end we might not have time. We might be rushing for the next speaker to go on. We might miss out the chance to have a question. So come on, let's hear some questions. Anybody? I need 3 questions, otherwise we can't start. So yes, sir. Yeah, that's a really good one. A really good one. So let's add that. Any classes in java.util.Concurrent we should avoid like the plague. You like plagues in London, don't you? You haven't had lots of plagues here, I think. So. Okay, another one. That's a great question, thank you.
What's the SP velocity of an unladen swallow?
Okay, that's a good one. An unladen swallow, right? Something about threading, concurrency, something you've been wondering about. Why are you here? Yes, Jack. Oh, no, not Jack. Okay, Jack, go on. Oh, that's a good question. That's a really good question. Which of the classes has changed the most? Okay. Now, all right, one more. That's a great question too. How much do you have to relearn with virtual threads? So this is a really great bunch of questions. I need to start with the second answer, and then the first answer I'll show you a bit later, and the last one I'll tell you at the end of the talk. Right, so the second one, which is which of the classes changed the most, I'm not 100% sure, but I would think it's probably concurrent hash map. Because it's changed from Java 5 quite substantially internally. It used to use, first of all, it used to use reentrant lock for the locking. It changed to synchronized in Java 8. They also used to use only a linked list of nodes for clashes, and now they use a red-black tree. So I would probably guess, without having substantial evidence, that probably the concurrent hash map has changed the most since Java 5. All right, let's start. So I'm going to start by looking at a class that we all know, java.util.Vector. This is not the Vector API, this is the very old class from Java 1.0. And when they wrote it, they had a certain model in their mind about how concurrency would work, and they actually had most of the methods synchronized. The method synchronized itself, which then synchronized on this, and but they missed some synchronization points. So for read-only methods, they decided to not synchronize. So for example, they had the element count protected, so any subclass could change it, but also they had the size method without any synchronization at all. And this was Java 1.0. They made the add element synchronized, but not the size. So what could happen is one thread could read the size, and it would never change, because it cached the value. And another thread would change it, but change it and add an element, but the first thread wouldn't see that change. This was Java 1.0. Then in Java 1.1, they introduced a race condition. Who can see the race condition? It's very subtle. They implemented serializable. And they just used the default serialization. So what could happen now is you could write the vector, and at the same time, somebody else could change it. And this could produce a race condition on the output. So in Java 1.4, they fixed that. And they also fixed the problem with the size visibility by making the size method serializable, synchronized as well. So synchronized on the size, and they made the right object synchronized. All right, so they fixed 2 problems. What problem did they add? Sorry? Throughput, well, that's a good point. They might have added some more contention, But they added a bigger problem. They added a deadlock, right? Because if you have two vectors that point to each other, and you serialize them from two threads at the same time, you could get a deadlock. I wrote about this a long time ago in newsletter 184, but my comment was this will never happen in the real world, because no one's going to be so stupid to have two vectors pointed to each other and then try and serialize them at the same time. I was wrong. Somebody did actually have that use case, and they fixed it in the IBM version, and that change eventually got into Java 1.7. So they fixed this by making a copy of the details of the vector, put them into a put fields object, and then once that's done, they would then write out without holding the lock. And that's sort of the principle that you don't want to lock whilst holding, or call a method that doesn't belong to you whilst holding a lock, such as the write fields. But we went over to Java 1.8, and here they have the for each method, which is synchronized. And they're calling the except method whilst holding the lock, which means that it's very easy to cause a deadlock with the Java 8 vector. You simply have two vectors, two threads. Each vector in the for each loop is calling, for example, contains on another vector, on the other vector. And so you can very easily cause a deadlock. And another deadlock you can cause, which has been logged, is if you have two vectors and two threads, and each of them does dot equals on the other vector, then you can also cause a deadlock. Again, you have a lock ordering problem. These might be deadlocks that are possible, but they're so unlikely, you've got to be so crazy to write code like that, that we don't worry about this. So I'm not going to log a bug for this. I also don't have a good solution for this. So what's the takeaway? First of all, thread safety is quite subtle. You don't really know, and the problems with our testing, we don't always expose the bugs, because you need to know what to test for. You've got to be crazy enough to have two vectors which point to each other. Then you have to have two threads which try and serialize that. You've got to think of that. I mean, who thinks of stuff like that in order to know what to find? So one of the things I did a while ago during COVID lockdown, when there was nothing else to do, we were banned from going to the beach on Crete, if you can imagine that. I mean, that's crazy. I decided to really look at the java.util.concurrent library in more detail than most people have done, probably in like ever, or at least for a long time. Now, the challenge with writing correct thread-safe code is that we don't really know when we break the rules. You see, we've got the rule book, the Java memory model, and it has a whole bunch of rules of what happens before, how things are supposed to work, how the visibility is, and it's all about memory. It's not about, there's no threading model as such. There's a memory model which says, how do we work with shared objects? But there's no way to test whether our code adheres to the Java memory model 100%. There's no such thing, unfortunately. We just have to run the code, hopefully on lots of different hardware, and check whether it works correctly. And some bugs are very, very hard to detect. Now, I live on the island of Crete, and I found out just the other day that there's a law, I didn't know about this law, that it is illegal to drive your car and to drink your coffee at the same time. And it's apparently only illegal in Greece and Cyprus. Now, I do see there's some reason for it, but I didn't know about it, because it's not enforced. I've never seen anybody get in trouble for drinking coffee. Maybe you get in trouble for not drinking coffee and driving, because you'll fall asleep. But yeah, so these are laws, but then if they're not enforced, you don't know about them. And it's the same problem with the memory model. So here's a bug that I discovered hidden away up in the database. And basically, it's a very strange bug that has to do with lock support. Now, lock support, when the class is loaded, it has to, well, sometimes the lock support loading mechanism can send an unpark to whichever thread is busy loading the lock support. So there's a very weird bug, or was a very weird bug. I don't know if it's still there, but I still haven't got clarity on this, which in some very strange circumstances could make it that certain threads that use lock support would get stuck. So you start your VM, and your VM starts up, but one thread is just stuck. It never gets unparked. And they found this at Google, and Martin Buchholz wrote a test that ran for a whole week of CPU time until it eventually showed this bug. So 1 week, so extremely elusive bug. And so they made this weird workaround where they put into classes, you can see the spread throughout the JDK. They've got 20 different places where they do this. They have a static initializer block, and then they simply say ensure loaded equals lock support.class. That just loads a class. It doesn't initialize a class, it just loads it. And this apparently solves the problem. Apparently. I think it does, because it does seem to change it, but I'm not sure whether it still is necessary in Java 9 onwards, because now the class loader references concurrent hash map, and that does this. So by inference, maybe you don't need this. So what's interesting, you're asking about virtual threads early on. Just a quick side thing. There are several places where virtual threads are being used where they don't do this. Now, I've logged a bug, but I'm not sure whether it's a problem to put it into the places where it's not in there. But I'm not sure whether it's actually a problem at all. So it's very elusive. And unfortunately, this happens sometimes with these bugs, that they're very hard to produce. Now, in the Java Concurrency in Practice book by Brian Gertz, he basically says that don't write your own synchronizers, use what's there. Not because we're stupid, but because more people have used their classes. And that comes back to the question by, I think Jack, no, not Jack, by the other question we had about which classes should you avoid, right? Avoid your own classes. Use what's there, and the reason is that more people have used the classes which are there, and so you have a better chance that you don't find that you won't stumble into some weird bugs in that. But the other thing is, when I heard this, I thought to myself, you know, there might be some value in studying these java.util concurrent classes in greater detail, because then you can see how they actually do it. What is this magic sauce that they apply to make it work? Also, you learn what is available. So I spent a lot of time on that. I've actually done some self-study classes, which are like 14 hours of learning just for 4 classes. So it's like really detailed, more than you ever want. Don't take them. You'll waste your time. You'll lose 14 hours of your life. But it's extremely detailed. Now, we all make mistakes, and it's good to have trust, but you need to also check that everything is correct. And this is a whole test-driven development idea, but it's very hard to do with multi-threaded code. And that's why I said we use well-known, well-used synchronizers. And with that, I don't even only say don't use your own, don't write your own, but also use the most common ones. So if you need a concurrent map, I would prefer concurrent hash map over concurrent skip list map. I've not found any bugs in concurrent hash map so far. I have found a bug in concurrent skip list map. Prefer LinkedBlockingQueue over LinkedBlockingDeck. No, but how many of you have used LinkedBlockingDeck? 1, 2, 3. Wow, that's a lot. That's like a lot. And anybody who finds bugs can report them. And I've reported quite a few. I didn't write them all down, but I put up a list on my website. And just to show you, for example, I found one in link transfer queue, one in thread lockerand, which is not really, I mean, there was a weird bug, very strange bug. Concurrent skip list map, I found one. ArrayBlockingQueue, I found one. But I know of some other ones which are not that serious, but they're like the deadlocks in Vector. And then I found 5 in link blocking deck, all different bugs. And so normally very few people, except for this crowd, use link blocking deck. They use link blocking queue. And so I've never found any bugs in link blocking queue or concurrent hash map. So usually the less used the classes, the higher the chance of bugs, which haven't been, obviously, I mean, we know this stuff. And so I also looked at how many times these classes are used in the JDK, and concurrent hash map is used hundreds of times. And then the other ones are used quite a few times: CopyOnWriteArrayList, concurrent link queue, concurrent linked deck, future task and LinkedBlockingQueue. Those are used quite a few times. I would use those in my code, and the rest treat with caution. They're not used as much. Okay, so that answers the first question. Concurrent hash map, LinkedBlockingQueue, concurrent link queue. Those are, I think, fairly safe to use. I'm not saying there are no bugs, but I just think there are less bugs than the other classes. Oh, I've got a little gift for those who are here. tinyurl.com/devox-uk-25. All that QR code takes you directly to the course. It's a data structures course I wrote a while ago. It's not a 14-hour course on 4 classes. It's the whole thing. But you'll learn a lot from that. Also, if you want to sign up to my newsletter, javaspecialist.eu, and as far as I know, mine is the oldest continuously running Java newsletter in the world, and the second oldest is Jack Shirazi's. So if you go to javaperformanceunion.com, you can sign up to his as well. He started, I think, 3 weeks after me, so it was like really close together. Both have been going for 24 years, over 24 years. All right, so let's look at a class here called striped64. And striped64, what it does is it allows us to increment values very quickly, contended values very quickly. So if we go to our code over here, let's go. Oh, that's the wrong one. Of course, I'd opened the wrong file. Let's open where's the right file now? Ah, there it is. Okay. There we go. So what we're going to do is we're going to compare incrementing 100 million times in parallel using atomic long and a LongAdder. So we're going to go instream.range from 0 to 100 million. We're going to say .parallel, and then we're going to make over here an atomic equals new atomic long, and we're going to simply increment this atomic. So we're going to say atomic dot increment and get. Okay, so nice and easy, 100 million times. And we'll measure the time, so we'll do time for that. And then let's run that and see how fast that runs. Now this is 100 million times, and we've got an atomic long, which is a wrapper around a volatile, and we're updating it concurrently with 12 threads at the same time, and it's using compare and swap. So it's 4.5 seconds to do this. So is it good? Is it bad? I don't know. It seems, I don't know, not sure. Let's do it again. This time we'll do it with an adder, LongAdder, and we'll do again our instream, range 0 to 100 million, parallel, dot for each, and we're going to say adder dot increment. And we'll do again a time around that to be the adder time, and we'll run that as well. So we'll see how long this takes, and the other one is 4.5 seconds. We'll see if it's, oh, wow, 84 milliseconds. So that's quite a big difference, isn't it? It's really quite amazing. So 84 versus almost 5 seconds. So how does this magic work? Well, it all boils down to something called striped64, because LongAdder extends a class called striped64. And this holds a number. It's hold a 64-bit value. And so what this whole thing is, it's about controlling a single 64-bit value. It's not a range of values, it's a single value. Sorry. And internally, they've got a thing called volatile long base. And the base contains a single value. Now what happens is, when you construct a new LongAdder, it's initialized with that long value, the volatile long. And if there's no conflict, that's all you're going to have. It's going to simply be one class with one long inside, and maybe some other fields as well. But it's going to be just one long. So it doesn't use a lot of memory. It's just one little class. The moment, and you'll then do a compare and swap on that value. Now, if you get a clash, if you lose the race on the compare and swap, what then happens is that they take a step back, they say, right, we had a clash on this long, let's make an array of cells. And this is why it's called striped, because it's called striped locking. So we now are creating individual cells. Each cell is approximately 128 bytes, so it's quite a big amount of memory. And they do that with something called contended. So this annotation means that it's going to construct the object to be larger so that you don't have false sharing. You don't have two objects living on the same cache line and then them both being invalidated at the same time. So this ensures that each cell is in its own cache line, and they also distribute the threads according to the cells based on some random function which seems to give us a pretty good distribution of threads. Now, interestingly, this actually comes from the thread class. So there's a thing called thread local random probe. This you'll find inside your thread. So if you go to thread, you'll see it there. There's your thread local random probe, and it's a hashing value that they're going to use to try and minimize the probability that two threads will end up on the same cell. Obviously, if you have 10 threads and they all update the same cell, it's going to be the same speed as an atomic long. But if you have all different cells, they're updating their own, and you have minimum amount of clashes. Now, what they do is they have a limit as to how many times they're going to make more cells. They'll start with 0 cells. Then they end up with 2 cells. Then they double it to 4 cells, double it to 8 cells. And I've got 12 cores on this machine. The maximum it's going to make is 16 cells. It will never grow beyond that. Even if you do have clashes and you lose clashes, because you might have, if a lot of threads, you might have clashes, you still will never exceed 16 cells. And there's a reason. Each cell is 128 bytes as a minimum. So if you have like 1,000 cells, it's going to take a lot of memory for this long adder. So that's how it works. That's how the details work of the Stripe 64. So, and of course, the takeaway is that it's best not to have any contention. If you can update locally and then later on join the values together, that's a better option. But you have to be careful with that, because if you write a test that simply goes 0 to 100 million I++, Java's smart enough to change it to I plus equals 100 million. Right? It's not going to sit there and 100 million times increment. It'll just say, you're trying to do plus 100 million, and it just does it. So just be aware that when you're writing tests to compare things, you need to make sure that you're actually doing the work and not just optimizing the code away. All right, so StartingGun synchronizer. Now, let's say I want to have a service that takes some time to start, and I've got other parts of my program that want this service to be started before they can run. So it's like a StartingGun. And so I want all the services to wait until the main service has started. And so I want to let them wait, but I don't want to deal with interrupted exception, because it's a pain. Nobody likes interrupted exceptions. And so what I've done is I've got 2 methods inside starting an interface: await uninterruptedly and ready. So once the service has started, I'm going to call ready, and then we're good to go. All right. Different ways we could do it. One way is like this, using synchronized. So I'm saying private boolean ready equals false. I make a synchronized method await uninterruptedly. I start the method by getting the current state, thread.interrupted, but that as a side effect also sets it to not interrupted anymore. So it resets interrupted flag, and I remember that, and then I say, while not ready, I try and wait. If I get interrupted, I'm going to catch interrupted exception, throw it away, remember that I was interrupted, and go back into the wait. Now the problem with wait is that wait doesn't really work very well with virtual threads before Java 24. From Java 24, they fixed that, so it's now working fine with Java with virtual threads. But this would not be good code if you're working with Java 21, for example. So, and then once we exit the while method, then if interrupted, I'm going to reinterrupt my current thread and exit from there. So you don't lose the status, but you wait until you're fully ready. And then you say, right, ready is again synchronized, set ready equals to true, and wake everybody up who might be waiting. Notify all. All right, fairly simple code, nothing too complicated here. Another way to do this is to base it on countdown latch. So I've made a countdown latch of 1, and the actual code looks quite similar. I'm again going to clear the interrupt. I'm going to call latch.await, and I'm going to keep on waiting until I have success, until ready is true, which, well, there's no ready, but until latch is open, and then exit, and ready will simply say latch.countdown. So this delegates to the countdown latch. Now, both of those will work. This one is slightly better because this one will also work with virtual threads because it's using park and unpark. It's not using synchronized and wait. But both times, if you get interrupted, you will cause interrupted exception to be constructed. Now, some of us really care about performance, and we don't want to have any unnecessary objects being made. And so we could try and optimize that away. And so what we could do, instead of doing it this way, we could actually look at how countdown latch works and then do the same. So let me quickly do that. So go to number 2. So here, I'm going to go to countdown latch and copy and paste the guts from this out. And you're actually allowed to do that. It's one of the only classes you can copy and paste, because this is part of the public domain. It's part of the java.util Java concurrency group. So copy and paste it out here. I'll put it at the bottom so don't. And okay, get count, we don't need that. Countdown. The countdown is basically our ready code. We're going to put that at the top. We're going to have over here, we've got our sync class. That's what we're going to, that's the guts of the countdown latch, right? And this abstract queue synchronizes what's actually controlling that sync. Now, this actually is a sync with size of 1. So what we're going to do here is to say, we're going to say a set state of just 1. So we just have 1 item. We don't need get count, and we need to override these 2 methods, try acquire shared and try release shared. To keep them the same as they are. And this is just going to be a sync over here equals new sync. Come on. Sync, we don't need the constructor because that's for having different counts. Await is going to change. This is basically going to be what we're going to put into the wait uninterruptedly. But you see that the sync has got 2 methods. One is called acquire shared interruptibly, and the other one is called just acquire shared, which is uninterruptedly. So we can just do it like this, right? And then the rest is, so await, we don't need that anymore. This is await with a timeout, we're not going to do that either. Delete that, and then there's a countdown, we don't need that either. And the toString, we don't do either. So we just have this over here. So it's basically, let's put the sync at the top. So we've got basically copied the implementation of the countdown latch into here. So this way we don't have interrupted exceptions being constructed. If you get interrupted, you're simply going to exit. In fact, you're going to wait until it's completed before exiting from there. It's an uninterruptible wait. All right, and so I've got a test to test it. StartingGun demo is this one here. Let's make sure it runs. Shouldn't make a mistake. So it seems to want to run. Which one is the best? My opinion is that the second one was the better one. Because with the second one, I am constructing an additional interrupted exception, but I am not working at such a low level where I can make a mistake. Right? I'm relying on the countdown latch. If there's a mistake in countdown latch, they'll fix it, and it's going to fix my code too. If I do my own thing, If there's a mistake, no one's going to fix it for me. All right. So, okay, then I mentioned that LinkedBlockingQueue is a class we use quite a lot. And this LinkedBlockingQueue uses something called a split lock. So you've got two different locks, one for the putting and one for the taking. Now what that means is you can put and take at exactly the same time. The two threads, one can put, one can take. Now that's amazing. But it does cause a problem, because if a thread puts and somebody else takes on different locks, how do they ensure visibility of the data they've just written? Because it's different locks. So they use a very sneaky trick where they store the count inside an atomic integer. Atomic integer count is volatile inside. And so they piggyback off that in order to make sure that the changes are visible in the right place. And it is quite interesting, because what it does is it gives you better throughput for the single producer, single consumer case for the LinkedBlockingQueue, but for the single producer, multi-consumer case, it's not necessarily as obvious. So if we do another quick demo here, what we're going to do now is we're going to make 10 million integers and put them into different types of blocking queues. We're going to test, first of all, a new linked blocking queue, right? And so the test is going to do this. It's going to be just a blocking queue test of integer. Let's call it queue. And we'll print out the type of queue, get class, get simple name, and then we'll do 10 million objects, and we're going to do the same object. Oh, it's even doing it for me. There you go. Is that nice? I did the demo 2 days ago, so it's like just remembered what I did last time. So basically, we're going to do this, stick this into here. I actually want to use a cached thread pool, just a bit easier. And then we'll do it like this. Okay. All right, so the first one, we're going to have 10 million puts. And then we're also going to have 10 million takes. So 10 million q.take. And I'm going to say put 42. So I don't make integer objects. I don't want to have that cost. Because if it's between minus 128 and 127, it's always the same cached object for the integers at the moment. That will change one day, but for now it's like that. And we'll measure the time as well. So the time for all of this, let's run it. So it's our LinkedBlockingQueue, 1.3 seconds. We should do it a few times, so let's do it 10 times, just to get a bit more warm-up. And we'll see how it does 10 times. So 1.3 seconds, or 1.7 now, 1.5. So what we should do is to also, see it warms up a bit. Whoa, that's a lot faster now. So what's happening is that garbage collector is interfering a bit. We'll do, after we've done each test, we'll do a system GC, which we don't normally do. It's a really bad idea. In fact, there was a specific bug that they had with the LinkedBlockingQueue, where when you did a system GC in an older version, it would pop the head into the alt space, and then all the objects would be pulled up there. So looking about 1 second for the LinkedBlockingQueue. Okay? 1 second. Now, if you do this with the LinkedBlocking deck, we see this. So it's a little bit slower, about 10% slower, LinkedBlocking deck. Because LinkedBlocking deck doesn't have 2 locks. It has 1 lock for the head and the tail, because it's got two ends. And so it's slightly slower than the LinkedBlockingQueue for this case. So for single producer, single consumer. Let's take the ArrayBlockingQueue. We'll make it 100,000 long. So it'll just block once it. And this actually is roughly the same speed as the link blocking queue at the moment. Okay. All right, now we're going to change it a little bit. We're going to put this into a constant. That's the elements. Okay. And we're going to have here int number of consumers equals 2. Let's call it J, number of consumers. And we're going to make 2 executors here. And we're going to say elements divided by number of consumers. This has to be, of course, divisible. All right, so we're going to have 2 consumers. Let's run it on the array blocking queue. Wow, look at that. So I've got 2 threads which are pulling things out very quickly. There's, which means there's never, with the ArrayBlockingQueue, there's never a case, or hardly ever a case, where the queue is full and the produce has to be blocked and has to wait. So that's good. That's 320 milliseconds. That's very fast. Let's try the link blocking deck. Also quite fast. Wow, pretty good. Again, same reason. Well, not exactly the same reason, slightly different reason. And then we look at the link blocking queue. Look what happens. So the link blocking queue actually ends up being slightly slower. Okay? And, well, most of the time it's slightly slower. And if you added some, so I've got a little, little thing I've written called a benchmark. So bm.start, let's call it bm. This is, let's call it, and then bm.stop. It will print out over here, producer bm. And we'll do the same thing for the consumer over here. We'll do a benchmark start and stop. I need to write a shortcut for this as well, like the other one. And this time we'll print out the consumer 1 and 2 of, and what this does, it measures the CPU time, user time, and memory allocated. So consumer like this. So what you'll find is that the producer, it allocates lots of memory. There's, of course, all the 10 million nodes that it allocates. The consumer doesn't allocate very much at all. But what you'll find is that if you, in fact, there's something wrong here. What have I done wrong here? Not to q.take. Something wrong with my output. It shouldn't say 0 there. Ah, yeah, thank you. Thank you. That's why. That, of course, doesn't make any sense. Right. Now you should see some memory being allocated as well. And these 28 megabytes here, these are being allocated by the locks, by the contended locks. So contended locks allocate memory as well. Okay, but you see a lot more time being spent on that. And the place you can find this actually is if you've got a fixed thread pool. The fixed thread pool internally uses a link blocking queue. So if you take a fixed thread pool of size 1 and you give it 10 million very small jobs to do, you'll have exactly this. What happens is that the producer adds jobs without any contention. The consumer can pull the jobs out without any contention. So you can have very high throughput on that. But if you have 2 threads in the fixed thread pool, the producer that's putting jobs in can still put them in without any contention, but the 2 threads which are taking the jobs out of the linked blocking queue now are contending with each other and are slowing each other down. And so you end up with quite a long queue of jobs which haven't been done yet. So your queue gets long. All right. And yeah, so a couple of other things. I just want to quickly show you one thing here before I go on, and that is I had a note for that shows the locks in NQ and DQ. So if you look at the link blocking queue, there's a thing called NQ, which assumes that the lock is held, and this you'll find inside the offer and add and so on. Not this one. That's not interesting. I think this one is the right one. Yeah, inside put, for example, you hold the put lock, and then you call NQ. And this then sets last equals last.next equals node, and then DQ removes it from the head of the node. Now, one of the things I do here is the h.next equals h. Whenever I see a comment like help GC, I worry, right? Because do you really need to help the GC? Is it really that necessary? And actually it is. This one is necessary. Because if they didn't have that, if they didn't have h next equals h, then you would get exactly the problem I mentioned, where if you make a list, a link blocking queue, and you do a system GC, then then your head node would end up in old GC, and then you have a link between old and new, and you end up sucking all the objects into old, and then you end up with having lots of full GCs in order to run. So, and I didn't believe it, of course, so I went and sort of compiled an old version of this to confirm it, and it really does make a big difference, a huge difference. I spent far too much time on this, way too much time. Yeah, it's fixed. Yeah. That's why they have that link in there. Okay. Now, the ArrayBlockingQueue I thought was going to be really simple, because it's like just basically a circular array list, not a big deal. And it is actually quite simple as these queues go. It's just one array, and the array, it's thread safe. Now, what you can do, for example, you can make an ArrayBlockingQueue, you can add 5 elements into it, you can make an iterator, you can start iterating, and then you can change it. And you can continue iterating, and you see all the values coming out, 4, 5, 6, 7, 8, 9, 10. And that's all fine. The problem comes in, what happens if you go past the end of the array, back onto the array, and you overwrite the data that's there? This is not a problem when you have a linked node structure, because you simply throw away the old nodes. You're not overwriting the nodes that are there. But with the ArrayBlockingQueue, it's one array, and it can be like a snake eating its tail going round and round. That's going to be a problem. And so what they wanted to do is to be able to manage that, and they've actually got a way of notifying all of the iterators that it's changed. How do you do that? Well, it's weakly consistent, which means that you can change it whilst iterating and it won't give a concurrent modification exception. But they have to also somehow keep track of the iterators. So the way they do that is with weak references, which has nothing to do with weakly consistent. It's just the same name. But let me show you how that works. So here I've got your demo. You've got 1, 2, 3, 4, 5. What we then do is we print out the first 3, we add another 5 elements, and whenever you have an iterator, it always caches the next item. So that's why even if we delete the number 4, it would still show 4 because it's at that position. So what I do now is after I've added these 10, I'm going to remove and add another 20 items. Okay, and if I then print for each remaining, I get nothing. Sorry. So you see over here, it just says number 1. So and that's the cached value that would be inside the iterator anyway. And if you look inside the iterator, the way that it's constructed, when you start it, it registers itself with a thing called iterators, and the iterators then has a node that is a weak reference. So this way they can keep track of all the iterators that are out there. It's the only class like that in the JDK, where they keep track of the iterators. Otherwise, normally you couldn't do that because you'd cause a memory leak. So that's how they do it there. And it's super complicated. I never expected that to be that complicated. Okay. Then the CopyOnWriteArrayList, this is another fun one. They try to avoid locking if they can. So the idea with CopyOnWriteArrayList, whenever you change it, they make a copy of the underlying array. So if you, for example, remove an item from the array, they could synchronize up front and say, right, you want to do this, let's synchronize and remove the element. But they only want to do that when they are sure that your array actually contains that item, right? So that's what they do. They basically say, I'm going to say, get the array that gets an object array snapshot. If they search for the item, and then they say return index is greater than or equal to 0, they have found it, and then they do another remove, which is synchronized. Now, I'm going to show you some code that I hope you have never seen before. Okay, I'm going to show you something that I didn't know is possible to do, and I sort of wish I didn't know it was possible. All right? Are you ready for this? You know, when you're looking at the java.util.concurrent library, it is always a bit dangerous. Watch this. So here's a synchronized method, synchronized on the lock. And here we've got an if statement. Basically what they do is we re-get the array, and if the array is changed, then that would have changed, and then you would know that you need to now search again. But look at this. If the snapshot is not equal to current, they've put a label before the opening curly brace of the if statement. Now, we all know what labels are, right? It's for basically go-to in Java. How many of you have seen something like this, where you have if and then a label and then the open curly brace? You've seen it. Wow, okay. Now, I've seen labels, but I've not seen labels like this. I've never seen labels in the middle of an if statement. So if statement and then the label over here. And when I looked at this, I thought, this is nuts. I mean, this is like someone really protecting their domain. But everything is very deliberate in this class, these classes. And what they're trying to do is to minimize the amount of duplicate code in order to make it easy for the hotspot profiler to compile the code. That's at a level that I don't operate. I mean, I try and make the code understandable. And I actually tried to refactor this a bit to make it read better. I didn't come up with anything that I was completely satisfied with. So if you want to try and make it better, improve it and submit a bug report, and maybe they'll accept your change. That was quite a fun one. So we've got another minute and a half. There was one question which I didn't really look at, which was how much do we have to relearn with virtual threads? Not too much, fortunately. With basically most of especially since Java 24. Before Java 24, there were a few things you had to be careful of. Because before Java 24, you can't rely on wait. You can't use wait and notify. But since Java 24, you can. And there are some places, for example, in concurrent hash map, if you do, for example, compute if absent, internally it actually uses a wait, and it'll actually park you. And so if you're waiting for a long time, you can use up all your, in fact, I think it's not even a wait, it's a park. So you actually can use up all your carrier threads that way. Because you're inside it, you're pinning the threads. And since they solved that, it's not a problem anymore. So if you work with Java 24, there's not much you have to worry about. But before that, yes, you do have to worry about it. So don't forget, if you haven't got that yet, grab it. And we have another 20 seconds. Thanks for joining me. Can I quickly take a picture? Because I will never, nobody will believe that this is all for a concurrency talk. This is like, I need to actually do like a pano, because this is just not going to, okay, everybody stand still for a second. Pano through you, because this is crazy, amazing. So thank you very much. I hope that Mark will invite me back one of these days. Enjoy the rest of the conference.